Got to fit recitation in.
Be like your first class, then lecture, then recitation, then lab. It's an hour earlier. 4:20. See what's going on here, Marissa.
I didn't plan that. I swear, I'm just trying to pack in the classes and avoid schedule conflicts, which still failed.
Yeah, I'm sorry to say it's the only time that our class scheduling. Deciding with this one.
I don't have a lot of confidence in my brain by Thursday afternoon.
Yeah, just like the second reference might be, but they'll probably change after like the first week.
Yeah, I have plans to get April. Okay. Yeah. So at the end of the term, I never get to stay in my routine. Oh no, it's like the best one.
Oh, yeah, you're curious. It's like, I know.
And focus.
Yeah.
I mean, I wanted to do it. Oh. I wonder if Marianne could, like, she actually did bring that up.
Where is it? Is Amanda in the class this time?
She is.
I was like, we'll just go there. Seems right.
And then, so those who snuck in, if you wouldn't mind, if you want to change lab sections, so I want you to write here like what lab section you want to be in, and then just let me know if you're registered or not for that section. I'll go over all the details as everyone shows up. feel like we're missing a lot of people. Is there like a class that conflicts? Does anybody know by any chance? I'm just curious. All right, I'm going to take roll formally. I don't normally do that, but there are a few new faces. And then if I butcher your name, just let me know. If you go by something else, just let me know. So Echo, I don't see Echo today. Nikki A, you're there. Molly, Izzy, Logan is not here today. Adrian Gonzalez not here today. Amanda, we're missing everybody. Eve, there's Eve. Jana, do you know anything about Derek? No. Okay, no Derek. Alexis, you're here. Allison, okay, oh wait, I don't know you, Allison, welcome. Yahira, no Yahira today. Jana's here. And then, oh, there's Echo. And then Allison Myers, but I think Vaughn, preferred name, no Vaughn, okay. Keenan, no Keenan. Jared, there you are. Sierra's here. Alicia's here. Josue's here. Michaela. No Sophia today. Or yet Cassandra's here. No Alexis Taylor. Carl's probably online. Oh, there's Derek. We were just gossiping about you. And Caitlin Straight. So I don't know you. Welcome. And then you've got my email, so re-register. Okay. I'll make an announcement, but yeah, re-register. Dominic is not here today. And Kailani is not here yet. Oh yeah, she's coming. Okay. And so if you can see on the board, and I can let me write these down. So my grand plan, those of you who are with me in fall, I was trying very hard to get a Thursday lab section opened early to avoid the drama, and that absolutely failed. So if you are on the wait list, there is no wait list. The clerical errors, people didn't get moved over, so now you have to register. And I truly apologize about this. I knew this was going to happen, tried avoiding it, didn't work. So if you need to register for the class, if you are waitlisted, that means you need to re-register. So you can use that code CGGU. It's also on the board. And then recitation, same thing. Register, so NEGJ. And then so my next ask is, so one, you need to be registered in a lab, especially before, I forget what the deadline is, I think Monday the 9th. So must be registered, and this goes for all your classes, by January 9th. So if you are not registered by January 9th, I think you will have financial aid issues is what they're saying. So please register. And so this means throw yourself into a lab section, and then I'm trying to sort out the details again because we didn't have the lab section. And so right now I only have one person officially enrolled in Thursday, and if you want to be in Thursday, I will ask that you sign up here just so I know that you will be present in class and who to expect on Thursday, because right now we have too many people in the Tuesday lab, so I need some people to move over, so at least probably like 3 or 4 people. So welcome, Carl. So if you could sign up if you want to be in the Thursday section, and then it would be nice if you register, and so I'll put the lab codes. So lab for Tuesday is YKVS. If you want to get into the Thursday section, that's going to be SUVV. And so again, this one is full, but if we have some people moving around, then, you know, there's some flexibility here. But the main thing is get in a lab section so that you won't have financial aid issues. That's a big thing. Be registered for all 3 sections. And so most of you know the drill. You have to be in all 3, lecture, recitation, and one of the labs. So again, just get yourself in there. And I would prefer, so this week we have lab. It's relatively easy. It'll just be like online on the computers. And so I would prefer that if you show up to whichever lab you want to be in the quarter. So that way we can kind of see, like, you know, if we have 27 in the Tuesday, we're going to have to do some, you know, finagling because we can't fit everybody in. So that's the big thing. But there's plenty of space in lecture and recitation, so if your friends aren't enrolled, they can still join. Again, there is no wait list. That's just a clerical error, lie, and I apologize that we can't just move you off. I can't do anything other than tell you to re-register. All right, does that clarify registration and all that? And so the Tuesday lab, just so people know, it's from 1:30 to 4:20. And then the Thursday one, it has to be a little later because we have to fit recitation in. There. And so sneaking into your Vaughn, right?
Yes.
So Vaughn made it. And your last name is Myers, right? Okay. And Kailani, or no, Alexis, sorry. Alexis snuck in. And Sophia. Anybody else sneak in that I missed? Oh, Amanda, got you. All right, sweet. Any questions about that so far? So let's talk about your big project of the quarter. And so you probably already know this, that it's coming. So if you remember last fall, right, we had our little abstract on a topic. And again, if you weren't here, that's fine. All you missed out was people did some initial research on trying to find a potential topic to write a paper on. And so now winter quarter, our goal is to write a rough draft of our paper. And I'll post more details online. So you'll see this pop up on Blackboard. And so essentially, you don't have to pick the same topic if you don't like it. So that was why we kind of did those initial abstracts, you know, do some initial reading. Do I want to write a paper on this topic? You're more than welcome to change topics. It doesn't matter to me. And again, rough draft. So probably looking for around 2 to 3 pages of something going. And then the goal, so where we're headed with this is spring. You'll have the final paper, which should be easy if you're just cleaning up your rough draft. And the final paper will be 5 pages. And then at the end, we do this kind of poster session presentation. So if you've ever been to a conference, it would be like the same thing. People have their posters, and then we'll kind of rotate. Half the people present, and the other half look around and listen, and then we'll swap. Probably do some light refreshments, you know, something fun for the end of the year. And that'll be a project. So that's where we're going. And so I'll post this out on Blackboard soon, but I'll do a paper topic, a paper check-in for the quarter. So probably this will be due at the end of week 3, just how's it going? And then you can retell me your topic. Again, doesn't have to match. Can be anything related to chemistry. You can talk to me individually, and then just what sources you're using. And so that will be due coming up, again, week 3. That'll just be like a quiz assignment. Right. Any questions about that? And then Blackboard, so how the class runs, yeah.
Is it going to be an expository, like presentational writing paper, or is it trying to argue for something in specific?
It's just more like explaining the research, so, and you don't really have to argue necessarily, you can just like present what's going on, like, you know, if you wanted to do solar energy, you could just talk about the pros and cons of it. If you wanted to argue for or against it, like, that's fine, but, you know, I'm more interested in like reading a paper, kind of doing your research, so it's more like a research paper. And so I guess we'll go over, just in case, so the course will be run about the same. And so homework, I'll hand out homework on Tuesdays, and then it will be due on Thursdays, again in general, and you can turn homework to me either in person or online. And then just like last quarter, we'll have our quizzes right during recitation. And so we will actually have a quiz on week 1, and it will just be Lewis dot structures. It'll be open book. I can't remember if Dorothy said we're doing open partners, so maybe we'll do a partner quiz to start off just the first week. So that's just first week, so that'll be this Thursday, and it should just be a review from your Lewis dot structures. And we'll start reviewing more today anyways. And then, so as usual, you'll have exams. And let me pull up the syllabus. Blah, blah, blah. You have your percentages here, so your paper draft will be worth 5%, and then we took it from the exams, so exams are only 40 this quarter. Hopefully that makes people feel better. And so we'll start off, we have our lab, week 1, with our model building. Again, that'll be online, and also with the model kits today. And then you can see pretty similar schedule. We'll have our first exam on week 6. And we'll have no lab that week. That'll be the lab makeup time too. So if anyone needs to make up an in-person lab, we'll do that week 6. And continuing on. And then week 10, you'll have your rough draft of your paper due. And then notice we'll have our lab practicum and checkout on week 10, just like we did last quarter. Any questions about how the course runs? And those of you who have been in my class, you know, email is the best way to reach me, so I'll just say that again. Email is the best way to reach me. If you send me a course message, I may not look at it for a couple of weeks since I don't get any notifications. So email is best. I'll rewrite my email in case anybody needs it. Just watch the spelling. What else do I need to say? And then, did everyone get my email so you know that I also YouTube stream this directly to YouTube for all your convenience? I do it to YouTube, so I don't have to upload and download any videos on Zoom. It's just straight there, available to watch right after lecture. So in case you miss, or like I said, I know there's some conflicts, so you can always catch up on lecture there. All right, I'm ready to dive into chapter 8 then. And so before we dive in, I have a handout for you. I think I handed it out last quarter because I got too excited, and then I forgot that we don't do geometries until second quarter. You hung on to yours. Saving paper then. All right, so if you were with me last quarter, you knew that I was trying to get you to see the 3D shape of your Lewis dot structures as we drew them. But that's really what we're doing this quarter is now we're going to kind of re-go over how to do our Lewis dot structures, but really emphasize our geometry this time. And so we'll start off by going through these electron pairs. But let's kind of look at what they have. So we have our kind of our key family here. And so if you have 2 electron pairs, that basically means you have 2 things attached to some sort of central atom. And so we'll go through this whole pattern. So 3, now you have 3 electron pairs, aka 3 things attached to it, so either atoms or lone pairs. Again, we'll go into all these in details. And then 4, 5, 6. And so let's start off. And so we'll start off with our, we'll call it our group 2. So 2 electron pairs. Oops. And so now this is going to be general A, X2. So you have some sort of central atom with 2 things attached to it. And so the example we'll look at is actually beryllium chloride. And so who thinks this is funny based off of last quarter? Anybody bothered by this? What would you expect it to be? So this is a kind of funny one. So if we look at beryllium dichloride, we probably would expect it to be like an ionic compound because it's, right, our metal. Because we have a very classic, right, metal plus non-metal situation. And so you might think that it's an ionic compound, but this is why solid state structures are really important, is we actually see the true nature of beryllium chloride. And actually this doesn't even describe its true nature. So if we look at it in the solid state, it creates more of this tetrahedral pattern. But for our case, we'll just look at it in kind of this simplified view. And so we see, right, central atom, 2 things attached. And so what's also kind of funny about this structure, so it's essentially missing valence electrons. Not really missing, but if we're just looking at, yeah, octet rule is violated. So beryllium, right, has 2 valence electrons, so it only brought 2 to the party. Chlorine has 7, so 1, 2, 3, 4, 5, 6, 7 goes into bonding. So obviously this is a little weird, probably why that solid state structure looks like this, again, to get some sort of data bonding here, but we're not worried about those details, so again, we'll just treat it kind of this more simple case. And so how many electrons would it have then based off of this drawing, beryllium? So only 4 electrons. And then, so the other thing that we want to look at is our hybridization. And so now if we just have 2 things attached to it, this is also sp hybridized, so it doesn't matter what it is, so sp. And so what this is saying, so do we remember what a s orbital looks like? Which one was the s orbital? Now we need to talk about hybridizations. What was the shape? Yeah, of S. So it's just a sphere. And so if we want to think about how it's going to look. So if it's sp hybridized, then we're going to take one s orbital plus we have a p orbital. And so just, again, kind of a refresher, let's get the cobwebs out. We have our 3 p orbitals. So this is, let's call this px going up and down. And then, so pz, I'll put in the shading, so pz would then be going along the axis. So pz, the z-axis is usually the principal rotation axis. So that just means whatever axis has the most rotational symmetry. So you could put this right on a rod and spin it infinitely, so there's infinite symmetry. And then of course py, I apologize that I can't draw, is coming in and out of the board. So just like that, py. So you have, right, 3 p orbitals. And so can you guess, based off of these drawings, which p orbital you'd probably want to add to our s orbital here? So which one runs in the correct direction for bonding? So pz, exactly. So we called this pz, and then so we're going to add our pz orbital, and then that's going to give us our sp hybridized. So it's going to look something like that, kind of a mix of an s and a p, which it kind of just ended up looking like a p from my terrible drawing. But you can see, so this would be our orbitals, and so this would be the orbitals of beryllium, and now it's prime to hook up with chlorine. And then so here they're just making a sigma bond. So sigma bonds are direct, so head-to-head, so, right, you have this head-to-head interaction, they're facing each other, and so that's going to be a sigma bond. So let's look at questions. So let's look at it. Sorry?
Where did the S orbital go?
It just kind of got, like, became part of this. So it would be like, if you could add it, you would have like more electron density here, plus you're also like helping with the phasing to just kind of make it our sp here. So let's look at another linear example. So what about CO2? So CO2 falls into this same general AX2 pattern. So take a second, draw the Lewis dot structure for CO2. So somebody tell me what your CO2 looks like. I'm looking at yours. Yours is drawn.
Double bonding to the oxygen on both sides.
Perfect. And then I like how you, so I'm picking on him just because I can see his drawing, and I can see it's drawn really nicely. Because he has the lone pairs here. And so now we're going to have to reach a little bit to analyze the bonding for a second. And so let's look at what orbitals we have available and look at how we actually make this double bond. And so I'm just going to draw our little lone pairs so we can emphasize that they're occupying space. And so let's just analyze the oxygen for a second. So I'm just going to redraw it. So we have our oxygen double bonded to carbon, lone pair, lone pair. So then based off of your Vesper chart, so which electron pair group is it in? So central atom, right, 3 things attached to it. So 3, so it's on our electron pair of 3. And I know we haven't gotten there. Obviously, we're headed there. And so if it's 3, that means that there are 3 orbitals involved in mixing. So that's going to be sp2.
And so why are there 3 pairs? There are only 2 lone pairs after the double bond.
So 1, 2, 3. So it's attached to the carbon. So this is considered, right, an electron pair. So an electron pair is, again, either just an atom or a lone pair. And so, right, we have 2 lone pairs plus 1 atom. So that gives us 3. So now our oxygen is sp3 hybridized. So we're thinking about the orbitals that went into it. So probably pz and px we'll say for formality. So this depends, on, again, on your orientation. But essentially now what's happening is we have our s orbital to get this sp2 hybridization. So we have our s plus our 2 p's, so pz plus px. And then, so that'll give us something that looks like that. So this is planar, just so we can, again, orient ourselves. So this itself is trigonal planar. We'll go over this again as we get to group 3. But then the next question I want to ask is, okay, well, what orbitals are left over on oxygen? Because we accounted for s and 2 p's. So what's left on oxygen? So pz, px. Also, if anyone's in the chat, just say hello so I know you're here. So what about, where's py? So we haven't accounted for py yet. So py, right, it's currently available. But now let's take a look at what's going on with carbon dioxide, and now we can explain why there's a double bond as well. So you can see we have 1 sigma bond, and so now I'm going to redraw this. So we have our carbon. So what's our hybridization on our carbon again? So it only has how many things attached to it, though? 2. So if it only has 2 things, it's an electron pair 2. And then what's the hybridization? Why'd you guys get so shy? You don't know each other?
I'm a little confused. What is the AX?
So the AX2 is just like the generic, what group it belongs to. So if we go back right to our chart, I'm just looking at here. So this would correspond to AX2. And I can't think of any examples right now. But basically, right, so AXE would be if you had some sort of molecule A with a lone pair attached to X. So that's all like the A, X, and E things. So E basically stands for lone pairs, and X is any atom. It's just for the lone pair 2, there's really only AX2. And then, so then we say, right, anything with 2 electron pairs is always sp hybridized. So I would write that on your chart, like this is going to be sp. There are 2 things attached to it, it has to be sp hybridized. So then going back, so what's the hybridization again on carbon? So sp, so because again, just 2 things attached to it. We're not caring yet why we have 2 double bonds. We're getting there. So I'm just going to redraw this, our carbon. And so this is, right, sp hybridized. So we have our 2 sp orbitals, right, they're primed, ready to bond. And they're combining with our oxygen, which we said was sp2. Let me just move this down a little. So then our oxygen comes in, right? It's sp2 hybridized. So sp2, sp2. So this is my sp2 hybridized orbital with its lone pairs, right? I'm just trying to show that the lone pairs are there. And then we have our sigma bonding is then made from our sp, right, being in phase with our sp2 orbital. So those will come, and that gives us our sigma bond. And of course, same thing happens on the other side. Again, all sp2 hybridized orbitals coming in. This is again planar, so you can imagine that. So they're planar coming together. So now we form, right, our sigma bond here. So that accounts for one of our bonds, but then how do we get the double bond? Where did that come from again? And what did we say was available on oxygen? So the other p orbital, and so formally we had called it py. Again, you could call it pz. Or px, doesn't matter too much. But we have our py here. So py is hanging out. And then, so what does carbon have available with its p orbitals? So it does. So it has, so carbon has, I'll draw py first, and then yes, it does also have px, just like you said. So that's just hanging out. So there's no one to bond with px, so that kind of explains why there's not a triple bond. So oxygen, right, doesn't have a px orbital. But they do have 2 py's, and so when they're in phase like this, we can create a bond. And so now this is through space interaction. Sorry, I want my highlighter. So now we have our bond here. So they're bonding, they're in phase, so that means that they're bonding. And so this means that this is formally a pi bond. And so we have 1 pi bond, 1 sigma bond, and that's how we get our double bond. So our double bond is then made up of a sigma and a pi bond. course, so same thing, right? This can also, it can be delocalized across, so we get, right, our double bond on each side. So we have, right, a sigma on each side and a pi bond on each side. So is that starting to make more sense? Again, ask questions. Now's the time to ask questions. So now we'll move on for now. It might become more clear as we continue. And so now we'll flip over. So now we're looking at our 3-electron pair group. And so this molecule here, our trigonal planar, would fall under AX3. And so we could look at a few different examples. So let's look at, so now we're at 3-electron pairs. And can anyone think of an example for AX3? Maybe another one of those funny ones that you might think is ionic but is really covalent. There's also other molecules that would fit under AX3. Yeah, you don't have any favorite AX3s? This is one of my favorite groups just because they're always angry, and I mean, you know why they're angry, right? They're electron deficient, so they're always angry, as I call them. So the ones I was thinking of is all our group 3s, and so that can be, right, gallium trichloride, aluminum trichloride, or boron trichloride, or the triethyl borate. Oops. So these are little ethyl groups attached to it. So any of these, right, all fit under that same category, just something with 3 things attached to it. And so let's just pick aluminum. I'm feeling aluminum today. And so this is one of those odd ones that we might expect it to be ionic, just based on our naming rules and what it is, right? Metal plus nonmetal. But if we look at it, again, in the solid state, this is actually a reflection of how it is. Plus, so aluminum trichloride, it's a solid white powder. And then if you take it out in the air, it starts fuming. It's reacting with, residual water in the air, and then it makes hydrochloric acid residually as well. So nice fuming, angry powder. That's why they're always fun to work with. So same thing, so boron, this triethyl zinc, it fumes like a green flame just in air because it's so angry. And so aluminum chloride should be nice and white. I don't know why they showed a contaminated version, but it's just this white powder. And so you can see the solid state is similar to beryllium, where even what we're drawing isn't a true reflection. So you can see, right, the aluminum, and then it does this weird dimerization thing. But for our purpose, we just kind of simplify it to this structure. And so what do we say was the hybridization of this? Do you remember?
Is this P2?
Yes.
Is this the chart that's on page 290 also in the textbook? I'm having a hard time visualizing.
What?
There's a chart in the textbook.
You said 290?
Yeah.
Let me flip there and see if our 290s match.
Sorry, you know how I like pictures.
Oh, pictures are perfect. Oh, I'm not sure my page 290 matches. Is it somewhere in chapter 8?
No, it's in chapter 9.
Oh, okay.
Table 9.3.
What?
Table 9.3.
Let's see, die point what? I would love to know what picture though you're looking at. Here, let me look at your book. Yeah, that's roughly what we're going for. I wish I could find that. So that's a good picture. Let's see if we can find it in here. Oh my goodness.
No, it says page 305 of his document, but 290 at the top of it. Sorry, Marissa, I did not.
Just trying to find this chart. Because it would be helpful. I think you're right. It's all the same information. I don't know why. Ah, finally. Okay, we finally made it. So now we're all on the same page, literally. So yeah, same sort of idea here. So there was our beryllium example, and you can see, right, our sp, which just kind of ends up looking like a p orbital, but, and now we're at sp2, and then, so they use the term steric number, and that's what your chart calls electron pairs. So again, that's just how many things are attached to it, whether it's lone pairs or things. Then it tells you the geometry, and so again, you get that nice 3-lobe picture. And then, so again, hybridization, sp2. And again, you can remember, so if you have 3 things attached to it, 3 orbitals, so an s and 2 p's, just like we went over before. And so let's try another one that also fits under here. So see if you can draw the Lewis dot structure for SO3 then. So what does that look like? Bless you. So keep drawing. I'll just, for those of you that didn't have me, or maybe all of us need a refresher. So how to approach these, I would say, right, how many electrons do we have coming to our party? So I just total up our electrons. And remember, this is valence electrons. So we have 6 from sulfur, 6 from all the oxygens. So 4 times 6 gives us 24 electrons. So no matter what you do, please put 24 electrons in your structure. That's the biggest way to get full points or to start going down a path you don't want to go. So now that we know we need 24 and start drawing things, so probably just stick sulfur in the center. You can always start with 1 bond to each. Oops. And so then you could kind of play with it. So what do people get for bonds? How many bonds we have? Yeah.
6.
So you put all double bonds? So let's look at that if we like it. So a lot of people like this 6 bond. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24. So that looks pretty good. And if you played with other variations of that, you would just have to have formal charges. But this looks like a good structure. And then, so how many total electrons does sulfur have? So 12. So sulfur, 12 total electrons. So again, if you had me last quarter, we saw that we usually identified how many electrons are on the central atom, just how many it's feeling. And of course, once again, 3 things attached to it. Doesn't matter if they're double bonds or single bonds with different resonance structures. We know the geometry. So what's the geometry for these guys? And check your chart too. So they're sp2 hybridized, which makes them, so what's our geometry? So trigonal planar. Exactly. And so again, that just goes for all of these AX3s, they're all going to be trigonal planar. So now let's pop over. So we're still on 3 electron pairs, but now we do have an instance where we could have a central atom and a lone pair and 2 things that's attached to it. So we can call that AEX2. And so one example of that is SO2. So take a few minutes, see if you can draw the Lewis dot structure for SO2 and what that looks like. And then I'm going to go ahead and hand out homework before I forget so everyone has a copy. And it might look pretty similar. I see some molecules that we're doing right now, so you can go ahead and fill those in too. Do you need another copy?
Oh, no.
So I saw one I liked in the front. So again, I'll just start going through it. So we have to figure out our total electron situation. So 6 again for both of these with the valence. So 6 times 3 gives us 18 total electrons. And you kind of have a hint here, so you might know what it looks like. And I mean, that's the point, is you're supposed to start to recognize what it's going to look like based off of this geometry. And so I saw a structure that looked something like this in the front row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That looks good. And so let's see. We have octet rule is satisfied on oxygen, and then how many electrons are on sulfur here? So 10. So it feels those 10 electrons. And then what's the geometry then? Or let's start, so what's the hybridization? Yep, so it's still sp2, so we haven't left our 3 electron pair group yet. And then so we flip over, so it tells you the geometry, but this geometry actually has 2 names. So if you look at your chart, it just says bent, but other textbooks will make a distinction. So if you look, let's go back to this chart. So if you look, and if you maybe remember water, so there's 2 different bents. So we have a bent that's from the 3 electron pair that we're looking at right now. And then if you recall, water is also bent, except water has the 2 lone pairs, which we'll get there. And so you'll see some textbooks make the distinction that this is called V-shaped. And that's to more emphasize the different, harsher angle. So if you go back, right, this angle is 119, so it's a little bit wider than the smaller bent angle of water, since it has those 2 lone pairs and repulsing it. So this one only has 1, and it's just shy, right, of 120. So 120 would be if they were evenly spaced, but those lone pairs occupy just a little bit more, that it's closer to 119 there on the angle. But again, you'll see the terms V-shaped and bent used pretty interchangeably. So that's 119 degrees there. All right, so now let's look at our next group. So now we're looking at our 4 electron pairs, or if we're looking at a textbook here, so steric number 4. And so what's our hybridization? We can read it off the chart, or what is it? Somebody tell me. sp3. I'll start a new page. Now 4 electron pairs. And so if it's 4 things attached to it, that means we need 4 orbitals going into it. So of course now we have our S, our PZs going into it, PY, PX, I keep swapping my X and Y axes. And so that essentially gives us our 4 lobes that look tetrahedral. Let's pull up the picture since I can't draw. So again, those 4 lobes giving us the tetrahedral parent geometry. And so what's our classic tetrahedral example? So this would be AX4. What's our like favorite classic one? I like it. That wasn't what I was thinking of, but I love silicon tetrachloride. I love-hate relationship, but so silicon tetrachloride is an excellent one. I was thinking of methane, But either way, they're both part of the same electron geometry, so we can draw them both like so. Of course, chlorine now just has a bunch of lone pairs. And then, like I would do last quarter, we want to draw our wedges to show that it's coming out of the plane of the board. The dashes show behind the plane of the board here. So all these are sp3 hybridized on our central atom, so either carbon or silicon. And then, so these would be our tetrahedral geometry. And so that's the parent one. And so if we look at those angles, since they're all evenly distributed, it's 109.5 there. So look back, so this is our angles, so all evenly distributed, right? Atoms on there. And so now let's look at the next one. So what's a good example of AX3E then? So what happens when one of those is a lone pair? There's also a classic example for this one. Do y'all remember? Or an example? Still 4 pairs, so AX3E would be the designation for it. So basically, what has 3 substituents and 1 lone pair? It's one that we looked at a lot last quarter. Gotta clear all the cobwebs, too much eggnog. And no guesses? The one I'm thinking of is not sulfur. There could be a sulfur one that I'm not thinking of, but you're all gonna. What about good old ammonia? Oh, you see? You gotta say it. So, right, good old ammonia, our classic example. So it has our 2 electrons, so 1 lone pair, and then it follows, right, the same geometry. And so all we did is, right, swapped one of these substituents, turn it into a lone pair instead. Right, we could have even put ammonium here, just to really emphasize things. So, right, we have ammonium with our hydrogen here, then it gets deprotonated, or the base form is then ammonia with our lone pair. And so it still has, right, that basic tetrahedral shape, except what's this geometry called? And of course, now you can kind of see the geometry too, since it's, again, parent tetrahedral. Swap this out. So then what does that make this geometry? You can look on your chart too. Go for it. Yeah, trigonal. Can you tell the next word is? And kind of think about what it looks like, right? Chemists aren't that creative with their naming. So it's trigonal, right? But it's not planar. So what is it? Yeah, pyramidal or pyramidal. So I would say trigonal, pyramidal, or pyramidal, however you want to pronounce that. But yeah, right, so it looks like a pyramid because you started with your tetrahedral. Then you just took off our lone pair, but it's still in that kind of pyramid form. I'm telling you, chemists are not creative with namings, but should help you guys. So that's trigonal pyramidal or pyramidal. And then, so notice the angle on that if you look at your chart. It's a little bit smaller. So again, that lone pair now is repulsive, so it takes a lot of space, pushing down the hydrogens just a little bit to make that angle a little bit smaller of 107 there. And then, so looking at our next example, so now we're still in 4 electron pairs, but now it's AX2, E2. And what did we say was our usual example for this? You say H2O? I thought somebody said that. So H2O, I hope I wasn't just hearing things. So H2O is the example we've looked at a million times. So of course it has 2 substituents, 2 lone pairs. And so now we know that it's bent. So it's still hybridized, right? sp3 hybridization on our oxygen. And now our bent geometry. And so this is like the classic bent geometry. So usually when people refer to bent, they're thinking of the 4 electron pair water-like angle. And so that angle is 104.5 degrees. And so again, you can tell it's even a little bit smaller since now we have 2 lone pairs.
And are these SP3?
Yeah. Yep, so everybody in the 4 electron pair family is sp3. So if you want to put that, like wherever you need to write this, maybe on the side here. Okay, so we started with sp, then sp2. So these are all sp3. So all of these, right, are sp3. Maybe it's clearer if you look on here. So again, same thing, the steric number, all sp3 part of that family. So now let's look at some higher order. So now we're going into 5 electron pairs. So 5 electron pairs. And so now we have 5 things attached to something. That means we need 5 orbitals. So what's our hybridization? sp3d, exactly. And so now here's where things kind of start to get funny. So in actuality, there's no real d orbitals that are involved in bonding. So this is now just more kind of describing the shape of it, which is kind of annoying, but if we look into MO theory, we would find that are actually no d orbitals involved. We'll get there. If you're really bothered and want me to go over this later, I can do that individually, but right now, we'll just appreciate, 5 orbitals need to go in there and make our shape. And so the shape that it makes is we have something that looks like this. So 2 lobes up and down, and then the other 3 make that shape around the central. So you have 2 up and down, and then kind of your trigonal planar in the center there. And so let's look at it over here. So again, you can see our sp3d orbital. So again, right up and down on the z-axis, and then they're here on the x, and then kind of between the y there. So these are all p orbitals, though. And so let's start with AX5. So any guesses what AX5 might be, an example of AX5? Yeah. So PCl5. So phosphorus pentachloride is one of our classic examples. So of course phosphorus goes in the center, 2 chlorines on our z-axis, and the other one, so this one is in the plane, and then this one's kind of coming out of the plane of the board, behind the plane of the board. Don't forget your lone pairs, of course. And so let's just write our hybridization. So sp3d. And now what's the geometry of this structure? What does the name say? Slash, you can also kind of see it. So we have like a triangle, so kind of 2 triangles. And so what's the geometry? Exactly, so trigonal, bipyramidal. So, right, 2 pyramids essentially. Now let's try our next one. So now we're looking at, oh, and before we move on, and so you can tell that a lot of like the group 5s would fall under this. So any group 5 plus 5 substituents would all fall under that. So you could, go crazy with like arsenic, pentafluoride, and whatever else is in that group, right? Antimony, pentabromide, whatever. As long as it's, of course, phosphorus or below. So, right, in order to be hypervalent, we have to be on the 3rd row. That just has to deal with physical space, not with invoking d orbitals. So I can't emphasize that enough. It's like we are not invoking d orbitals in bonding. I don't know what your textbook said. I'd have to look at it. If it says d orbitals are involved, it's wrong. Like, there's no evidence for that.
So Marissa, on the homework where you asked for the shape, is that where you want us to put the trigonal bi?
Yeah.
I'm sorry, I
Bipyramidal or bipyramidal, whatever. Whichever rolls off the tongue easier.
neither.
Neither. Good thing it's not an oral exam, I guess. So AX5 even. So one example of that is SF4. So take a few minutes and just write the Lewis dot structure for SF4, what you think it would look like. So does someone want to describe their SF4, or how many lone pairs sulfur has, or how many bonds to each fluorine? So that's a good guess. And then,
4 bonds.
so there's 4 bonds. And that's all. I'm kind of go ahead. And so what I'm doing is I'm basing it off of this one. So this is right, our parent geometry. And so what happens if we just remove this chlorine essentially and it becomes a lone pair? What does that look like? And so that's the geometry for SF4. So this fluorine's kind of coming out of the plane of the board. This fluorine then would be behind the plane of the board. This lone pair is just in the plane of the board. And of course, it's going to create a little bit of repulsion there. I don't think that's a perfect 180-degree angle. And then, anybody want to say the geometry? So it can't be tetrahedral though, because it's, so sawhorse is correct. So sawhorse, so you can kind of tell, right, it looks like a seesaw. So you could call it sawhorse or seesaw, whatever one. So I usually call it seesaw just because that's what the playground thing is called. But you can see, right, it looks like a seesaw. It's got your little fulcrum in the middle, and kind of looks like it would do the seesaw movement.
Does it matter if I drew mine like?
Yeah, you could draw it. Yeah. I just drew it like this so it looks like a seesaw, but as long as you can tell that, yeah,
I
it's a
just copied the picture.
yeah, whatever works. So yeah, if you started with this geometry and then essentially just rewrote it and then just, you know, had a lone pair there instead of chlorine, that looks just fine. So let's try some other ones. And of course, it's still, right, sp3d hybridized, so we haven't moved on. So let's look over. So we did sawhorse. So now we need to look at what the T-shaped might be. Anyone know any T-shape? These ones are always funny. So this would be A, X3, E2 then. So all these will be T-shaped. And so some examples are going to be like chlorine trifluoride or iodine trifluoride, or sometimes you might see this like I4. And so all of those, you can tell they're all, right, group 7s with each other essentially. And so if we want to draw one, so let's just draw I4 for fun. I'm not sure that really exists. Let's see, so 7 times 4, so I need 28 electrons total in here. So where are we right now? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Uh-oh, did I miscount somewhere? 1, 2, 3, 4. So 8, 8, 8. So that's 24. Okay, 25, 26, 27, 28. I miscounted the first time. So we should have something like that. So we have 2 lone pairs. And so again, we could look at our parent geometry. So what happens if we essentially pluck off these chlorines and put lone pairs instead? That gives us this geometry right here. And so again, that was T-shaped. And you can tell it's T-shaped, right? It looks very T-shaped. Any questions on that one? And then so last one in our 5 electron pair example is this linear one. Any guesses for what might be linear with a bunch of lone pairs? We like briefly talked about this molecule, I think, but it's fine if you don't remember. So we're looking at AX2E3. Any guesses of what might an example be? If I give you a hint, it's with one of the noble gases. So how many can bond? And then how many compounds do you have? Any guesses? Any guesses? Okay, I'll reveal it. So xenon difluoride is kind of your classic example of this. So let's see. So we could either tally it up with our total electron count. So of course, xenon brings 8 to the party. Each fluorine brings 7. So that gives us, 14 plus 8 gives us 22. And then we can just start drawing our structure. So I'll fill in my lone pairs on fluorine first. And so this is 8 plus 8 is 16, and 17, 18, 19, 20, 21, 22. And so I put them, again, all around those central orbitals, kind of making that triangle shape. Maybe it's better to draw it the other way. Either way, just trying to help you all visually see geometry. So again, these orbitals are just in the center there. And so what's the geometry of this? So linear, and that's pretty easy, right? It looks linear. So that's all we need to say. And of course, it's still sp3 dehybridized. Oh, I guess lecture ends at 12:50, right? Well, it's 12:48, so I think we'll save the 6 electron pair for Thursday. Any last minute questions? Yeah.
On the homework, it asks if it's polar or non-polar. Can you go over how to figure that out?
So polar, you're mainly, if it's non-polar, you should find like symmetry in all directions. And then like non-polar, you're kind of looking for unevenness. So like xenon difluoride, right? That's going to be non-polar. So a lot of these are non-polar. So this one, so this II3 though, so this would, or II4 I mean. So this would probably be polar though, right? Because we have one side where you got some lone pairs. So you would have electron density there. And then so before everyone starts running out of here, if you snuck in late or haven't done it yet, so please let me know what lab, this is what lab you want to be in. So this is not what you're registered in, but I need people to sign up for the Thursday lab. And so again, if you weren't here, right, the Tuesday lab is 1:30 to 4:20, Thursday, right, 2:30 to 5:20. So I don't really care which one you're registered for, but we cannot have 27 bodies in one lab. So, talk with your friends, maybe get some. Awesome. So just write your name on here if you can do the Thursday lab or want to be there, just so I know who to expect. And then this week, please attend what lab you want to be in. It's okay if you're not registered yet. Just make sure you're registered in lecture recitation and A lab section by Monday so you don't have financial aid issues. So I'll leave this here. Yeah, please let me know. Otherwise, we'll be like rock, paper, scissoring and Tuesday.
So why would Xenon bond like if it's a normal gas?
So you can force it to do stuff. So, right, chemists, we like to make stuff do stuff. So xenon is so diffuse, it's orbital, so you can get it to bond. So that's why you have like xenon difluoride and then xenon tetrafluoride.
So it wouldn't happen naturally usually, right?
I'd have to look up like the abundance, of it. I'm not sure, but it could happen like naturally. Let's look it up. But a lot of the time, so.
I think both my lab partners are gone now.
Oh no.
They both dropped it.
Let's see. I'm trying to see if xenon difluoride is natural. Yeah, I'm not sure that xenon difluoride occurs naturally, because it talks about that it was first synthesized in 1962, so it may not occur. But there's always a question, like atmospheric chemistry is really weird, and sometimes you get some weird species in there that you wouldn't normally expect.
Do you know of any good resources, like exercises for building things like this, like online? Even like
I'm not sure. Actually, no, that's a lie. I might know of a website. I don't know if it'll be that helpful. I'll find it and maybe send an announcement.
They have that PhET simulator, don't they, for the thing? Like the Colorado one?
Oh, for which one?
For like geometry stuff? You're talking about that.
Maybe.
It's
Let
like
me
a
look.
PhET simulator. Because I remember doing this in like high school and all that. We'd like build it.
Yeah, we'll play with some of that in WebMO, but it's like not the same. All right, I'm going to stop streaming. Thanks for this.